Phanish,
Yeah.
are there any papers that integrate some of the features of NK models in a bandit model quite well that can be used as an example?
I haven't seen it. I can't remember. I don't think there is one that I remember at this point. There are some elements of the bandit framework in the NK model, like for example, softmax as a basis for choosing whether to believe the results of your local search in NK. There's a very well-known paper by Knudsen and Leventhal that does that. But the belief of updating element, the fourth element in this model, that combined with NK, I have not actually seen.
Okay.
Yeah. That's not a guarantee that it doesn't exist, but I probably would have seen it if it existed. I don't think I've seen it.
And the Knudsen and Leventhal paper is the two
phases of search. Yeah.
Two phases of search. Yeah. Okay.
Exactly.
Thank you.
Maybe the paper on analogical transfer on NK can be like a remotely related, because they learn some landscape and then compare their similarities, transfer some knowledge. It's the Gavetti-Leventhal series on analogical learning. I don't know. They're just, not exactly bandit and NK combination, but maybe some level of learning. I don't know.
Some kind of belief update.
Yeah.
Some sort, yeah.
Yeah, but I'm not seeing like a more explicit mapping between the two.
Mm-hmm.
So that also, there's one more thing I want to say about the relationship between these two models before we move on. So what we just discussed before the break was like a very explicit way of trying to capture aspiration-driven search and performance feedback into this framework. But a more sophisticated way of doing it is actually to do it metaphorically. Okay, so I'm going to show you how with, I think this is correct. I haven't thought it through in great depth, but I think without changing anything in the ARL framework, we can get most of the insight of aspiration-driven search already. Okay, here's how. So the key question is, what does alternative generation mean? Okay, we very mechanically modeled it earlier by saying there's a bucket of things that we haven't seen before, which we are going to reach into and pull out. But it doesn't have to be that explicit, right? It could be an action that was there in our set, but we never tried it before. These are two interpretations of alternative generation. So it's an action that is not in your set, and therefore you now reach in and pull it out. But behaviorally, it's the same as an action that may have existed in your set, but you just never touched it before, right? And that you would already get in this framework. So there can be actions here which have such low expected performance outcomes that you never ever touch them. So that's already possible here. So there is implicitly a kind of alternative generation idea built into the existing framework. Okay. You would still have to update your aspiration level. And now you could actually say that changing tau as a function of aspiration level is probabilistic search, not just probabilistic exploration. Metaphorically, they are the same. Why? Because if tau goes up, the chances of your picking an action that you never picked before because it has a very low attraction go up, right? All things being equal, if there was an action that was so unattractive, you would never have picked it under max. But under softmax, particularly as tau goes up, you increase the chance of picking it. So if you buy the idea that alternative generation is really the same as picking an action for the first time, then in fact, probabilistic exploration and probabilistic search are equivalent. You see that? So metaphorically, they can already be linked in the same model. We don't even have to go to a new model. And now the only remaining question is, do I still want to update beliefs or not? Okay, so interesting question here. Suppose we don't update beliefs in this last step. Is it still a model of learning? Yeah, Nettie thinks it's yes. Why is it still a model of learning?
I think it's because you're still changing your behavior. Yeah, that's a signal for learning.
You're still changing your behavior, and that behavior is changing because of changes in aspiration level, right? So this is really the point I wanted to drive home, that learning behavior, which is change in belief or behavior over time because of experience, can happen either explicitly through the beliefs about the actions or through the aspiration level alone, or both. Either alone is sufficient to make it a model of learning. Okay, so this is in fact a very simple tweak on our existing ARL model. So literally I changed nothing except I built in an aspiration level and I made my tau dependent on performance relative to aspiration level. With these two changes, I have another way of linking the two, which is more metaphorical than literal. Okay, and an interesting exercise might be to compare these two ways of doing it and see, do you really get anything new from being literal, or will the metaphorical one already give us what we want? Okay, my bet actually is that the metaphorical one will already do it, but I'm happy to be proven wrong. So you can try and check out both and see if you get anything qualitatively different. But I also wanted to make this point to show you that in the end, it's really underlining what I said earlier. There's no prize for literally capturing in a model the exact words that somebody said. Okay, that's helpful to increase our clarity. But in the end, the prize is on insight. So what did we learn that we did not have before we had a model? That's really going to determine whether the model itself is worth something or not. Otherwise, it's a fun exercise. It makes some things clearer. That's good for you. But our journals don't typically go for that sort of thing. I wish they did. It would make it easier for me to publish my stuff. But very often I am caught at the other end of the same problem, where the reviewers are saying, okay, cool new model, but like, what is it doing? What is it telling us we didn't know? You know, what pattern in the world is it explaining better? So that's always a good bar to try and shoot for. And maybe the simplest way to get to that bar is first work with the existing model and see if you can reinterpret metaphorically and see if that works for you. And if it doesn't, then you might start actually tweaking things in the model, right? So now you've seen two variants of how we can do this. Okay, I saw a hand up earlier. Nettie, did you want to ask something?
Yeah, just wondering, because you can like you don't know whether you have like new insights ex ante. So does that mean you have like tons of models in your drawer that's not published?
Oh yes, I have like many models that are unpublished. Many are like literally fun exercises I did over a weekend, and then I realized it was not going anywhere and I killed it. That's the advantage of working with models, right? The cost of prototyping is so small. I can't do that for an empirical project. I can't spend a month and then decide this is worthless. But modeling is really like a tool. It's a toy, you know, it's a set of toys that you can play with. And if something interesting comes, then you tell the world. Otherwise, you put them back in the toy box. So that's quite common. Okay, so I'm going to now talk about some of the concepts we need to understand social learning, but I will go through these fast because my assumption is you've done the pre-reading and stuff. So first concept is, what's interdependence between tasks? Okay, this is the definition. You've already seen this, hopefully. There are broadly three ways in which you can get dependencies between tasks. So common inputs, non-additive output, complementarity or substitution, and sequentiality, right? One can be an input to the other. All of these are forms in which tasks are interdependent. Okay, if you want an analogy, the first one is like a budget constraint. The second one is like complementarity or substitution in production function. And the third one is a variant on production function where it's sequential, right? One is an input to the other. So these are task dependencies. Is this clear? Do we need any clarification on this? It's fine. Okay. So what is decomposability or modularity? So decomposability is the term that Simon introduced, but it maps pretty much one-on-one on the technical property called modularity. And this is a property that is defined on a system of dependence that is expressed as a matrix. So if I can express the dependencies between a set of tasks where the rows are tasks and the columns are obviously the same tasks, it's a square matrix, and a one captures a dependency where a dependency can be any one of these three things, right? It doesn't even have to be a one. We can put a value between 0 and 1 or even -1 to +1. That doesn't really matter. The key point is, can I permute the rows and columns of the matrix to create a structure that looks like this? This is called a decomposable matrix, and this is also a modular matrix. So notice I have not changed the value in any cell. I have simply permuted the rows and columns. Okay. And if after doing this permutation, I'm able to find this kind of clear separation, then this is called a modular structure. Not the same as modularization. Okay, modularization is an approach to try to go from this to this, either by permutation or by willfully ignoring some of these dependencies or changing them in some way, right? We'll talk about how you can do that. But modularity is just a property of the dependent structure, and decomposability is really the same thing. So this is a perfectly decomposable matrix. Near decomposable would be something like this. There are just a few ones on the off diagonal, and non-decomposable would be something like this. This is okay? Yeah, clear? Okay. Now, that was dependence between tasks. That's not the same as interdependence between agents, between actors. Okay, so interdependence between actors means that given the task done by two actors, interdependence exists between them when the value of A's action to A depends on B's actions and vice versa. Okay, so dependency among tasks has been defined in terms of a production function. How the value of doing one task depends on other tasks being done. Dependency between agents is defined in terms of a payoff function. How the payoff to one actor's actions depend on the actions of the other. And this is not new to you. You've already seen this, but in a different form. You have seen this essentially in the form of payoffs in game theory. A payoff matrix in game theory is a way of capturing interdependence between agents, right? Whereas the matrix approach I just showed you is a way of capturing interdependence between tasks. So how do we go from one to the other? In the following two steps. So on the left here, you have a task dependency matrix. This is a task allocation matrix where we have allocated tasks to agents. And now that we know which agent is doing which set of tasks, we can combine all the tasks done by an agent and treat it as one super task. And we can then finally express a final matrix, which is between actors, and see which actors are dependent on each other. You see that? So it's like a three-step process. You start with the task dependent structure. You do a task allocation process, which is you put certain tasks in the hands of certain agents. That's captured here. That's why this was n times n, but this is m times n. This is a rectangle. And finally, you go back to a m times m matrix, which is the actors. And now what we are capturing here, this one is not the same as this one. This one is saying what are the dependencies between the set of tasks performed by actor 1 with actor 1, actor 2, actor 3, and so on. Okay. So this entire process is basically division of labor. Because first there's task division, which gives you this matrix. There's task allocation, which gives you this. And that results finally in a dependency matrix between actors. Is this transition clear, how this works? Yeah, any questions, clarifications?
Can you explain how do you go from second step to third step? Because the way I understood is that some actor would be assigned some tasks.
Correct.
So, and these tasks are dependent on each other. So let's say if the actor I is assigned 4 tasks, only 3 of them are dependent on the task assigned to another actor. So what would be right here, 1, 0, or like?
So that depends on whether you want to discretize it or give it a scale. So in the picture here, I've discretized it. So as long as there's some dependency between the 3 tasks I'm doing and the 1 task you're doing, I will count it as a 1.
Okay.
But it doesn't have to be. I could have made it like 0.75, right? Or 1 or something like that. That's just a matter of measurement. But conceptually, what's happening is you're moving from a matrix of tasks to a matrix of task versus people, and finally to a matrix back of people versus people, right? And the people versus people is the end product, which is dependence between actors. That's agent interdependence. Okay. We can talk later if you like about what do you do to actually change these ones here. How can I change the dependencies between the actors? That's modularization. And there are some tricks to do it. The most obvious way to do it is if you start with fairly decomposable task dependency matrix, then it's easy. Give all interdependent tasks to each agent separately, and then there will be no dependence between them. But suppose you can't do that because most dependency matrices are not fully modular, not fully decomposable, right? The world is complex. Then there are some tricks such as sequencing or measurement or buffering, by which effectively we can reduce the dependence between actors, right? So a very good example of this in software development would be that, let's say you're working on one part of a piece of code for a bank, Maybe it's the part which manages payments. And I'm working on another part of the code which manages, say, credit risk. Okay. There are going to be very dense dependencies between them. So if you look at the task dependency matrix, it will not be modular. But I can put in place something like an interface or a standard and say, as long as we are both adhering to the standard, our actions are going to become interdependent. So standards are a way of creating pseudo modularity, right? And we are doing that essentially by imposing it on the dependent structure. So that's really more of a topic for org design rather than org learning. So I won't get more into that for now. But as long as we are clear that in the end, we're going to be typically working with these things. But where do they come from? They come from this process. So the simple point being captured in this picture is dependency between actors comes from division of labor. Okay, that's really the point to make. And the division of labor itself has two components: task division. How do I chunk up the overall goal of the system into tasks, and task allocation? And the joint effects of these is to create dependency between actors. Now, this is all pretty abstract, and it's really helpful to think about this when you're dealing with systems with lots of actors. If it's only two, right, it's actually more helpful to think in terms of what are some standard patterns of dependency between actors. And there are a few very prominent patterns that is kind of helpful to understand these patterns of dependencies. So this is one way of showing dependence between two actors. Okay, so I have a set of choices I can make on this dimension. These are my actions. These are yours. And the payoff depends on our joint actions. But this is really the same with more choices than two as these. These are all dependency matrices, right, between actors. So it's telling me when I take one action, you take one action, what kind of dependence exists. So I'm going to take a couple of minutes to make sure we are comfortable with these four basic game types. You probably have seen them before, but these are, I think, very useful dependency structures to be familiar with, because many phenomena in organizations and outside organizations too have these kind of properties. So I'd like you perhaps to give me an example for each one of these. Okay. So the first one is the famous public goods or prisoner's dilemma game. That's a particular kind of dependency between actors, where you can see there's one Nash equilibrium, which is here. Okay, conditional on us being there, then nobody's going to switch. Even though if we were able to, we would actually do much better off if we could be here. But we can't because of the temptation payoff. So you're familiar with this game, right? So what's the situation in the real world that corresponds to this? Where do you see this kind of situation?
As in sticking to public goods, maybe like something like emissions right now, where each country is expected to do the higher, but need, as in everybody tries to defect. So we are at the Nash equilibrium, which is everybody is performing poorly.
Okay. Yes, so that's like a classic public goods problem, right? In a corporate context, if you wanted to look for something, it might be like a buyer-supplier arrangement, where it will be better for both if both invest in having high-quality talent and good technology, but both are actually better off if they don't invest and the other side invests. So the Nash equilibrium is nobody invests, right? This would be a case of a public goods game. Matching is the case where we don't really care which of these two equilibria we end up in, as long as we end up in an equilibrium. Right? So you might remember in research methods, we actually used a simple model of matching, where we show what happens when agents learn over time to coordinate in a game like this, right? What kind of situation does it capture?
Is it like coordination?
It's pure coordination, exactly. Yeah, it's a pure coordination game, right? So conventions, language formation is like this. We don't really care that much about what word we use to mean something, as long as we all agree on it, right? Driving is like that. So we don't really care whether we drive on the left or on the right, but we better all pick the same convention. Otherwise, we'll have trouble. So that's a pure coordination game. Okay, so some kind of standard setting within an industry or even within a company, we might be indifferent as to which standard, but we need to agree on one standard. So this is the kind of dependency structure being captured here. This is called stag hunt. This is an interesting one. We would be better off if we actually both picked A, right? Both picked action 0. So A picks 0, B also picks action 0. And there's no temptation to free ride here. So if I know for sure you're going to pick action 0, I will also pick action 0. So it's not like the prisoner's dilemma, right? There's no temptation payoff. But if there's a risk that you will not pick action 0, when I pick action 0, then I'm screwed. So think of this as different business units in a company. They all have to adopt some new IT standard. If everybody adopts, we're in great shape. No problem. And there's no temptation to free ride. But if I'm the only division that is first to adopt and nobody else is adopted, then I pay the costs and my division looks bad. So therefore, nobody adopts. So the reason it's called stag hunt is because the story it comes from is farmers can agree to meet in the morning to go hunt for deer, stag, and they'll get a lot of meat, or they can just stay on their own and hunt rabbit, right? It makes sense to go and hunt for deer together. But suppose I show up and you don't, because you were at home hunting rabbit, then I've lost the rabbit too. So that's why it's called the stag hunt game. And finally, the battle of sexes. So here there are two equilibria here, right? There's this one and this one. Here also there are two equilibria, by the way. Here there are two equilibria, 1.6 and 0.61. And both of us would prefer to be in equilibrium rather than out. But the problem is you prefer a different equilibrium than me. Okay. So the reason it's called Battle of the Sexes is probably a throwback to the sexist language of the 1960s and 70s. But the original story is that one partner wants to go to opera, one wants to go to football. Okay. Both would like to go together, but I would like to go to football and maybe my spouse would like to go to opera. If you want to reverse the gender roles, I want to go to opera and my wife wants to go to football. Something like that, right? But this is a canonical example of bargaining. This is bargaining, right? In bargaining, there is a bargaining zone, if you remember from your basic economics. And any point in that bargaining zone is an equilibrium. All points are, right? Every point in a bargaining zone is potentially a Nash equilibrium. Okay. The problem is we don't have the same preferences on where to stop in that zone. I would like it to be as close to my end. You would like it to be as close to your end. So we have to agree on something in between. So these are four canonical kind of problems. Free riding, the first one, pure coordination, risky coordination, stag hunt, and bargaining. These are, I think, not 100%. In fact, there are some studies which calculate all possible two-player games. Okay, but these really seem to capture a very large fraction of social situations. That's why very often these are a good starting point. If you're trying to model a particular situation of dependence between actors, you might start here. Now, we can also generalize this. I just gave you particular values in these cells, but you can write it more generally. Okay, you can actually just use parameters which can lie in some range and you can get the same game structures. Okay, this is actually done in detail in one of our papers that I've given you the reference of. Now, why is this useful for us to know? Let's think about situations where actors don't begin by knowing these payoffs, but have to learn them through learning by doing. Okay. Now, here's where it gets interesting. From the perspective of actor A, this is a learning by doing problem in which I have two actions, 0 and 1, right? And I have to choose which is the right action for me to take. But the complication is that the payoffs I'm getting when I take action 0 or 1 are not constant over time. It's not noise, right? There's actually a shift because it depends on what actor 2 is doing. So unless actor 1 and actor 2 can talk to each other and coordinate on what to do, each one is effectively doing learning by doing in isolation from each other without being able to communicate with each other, which means they're trying to learn which of the two arms of the bandit to pull with this kind of noise which is changing endogenously to their action, right? That's a full reinforcement learning task, if you remember from our discussion from last week. Said non-associative task, associative task. This is a full reinforcement learning task because the state is dependent the outcome I get for my action is actually dependent from my own past actions because it triggers what you do. So that creates a full reinforcement learning task. Okay. So just by adding one more actor and adding the assumption that they can't directly talk and coordinate and act as one person, the problem becomes quite complicated. I hope this point is clear, right? If there was no second actor, if instead of B, I replaced B with a random number generator. Okay, much simpler problem because then with equal probability or some fixed probability, one of the two actions will be taken, and I can learn that over time. That's the same as learning by doing with noisy feedback. Okay. But the moment the other is an actor, things get a lot more complicated because the feedback I get is contingent on what you do, but what you do is based on my past action. That's a full reinforcement learning task. So just by going from one actor to two, we have actually created a lot of complication. So this basic structure where two actors are interdependent, but don't know how they're interdependent, they don't know which of these games they're playing. They have to discover it through trial and error learning, through learning by doing, without being able to communicate with each other. This is called a coupled learning problem. Okay, so this is because their actions are dependent and their payoff depends on the actions of the others. So they have to discover through trial and error what actions to take. And they can do quite well actually in these situations. So given enough time, even though they can't talk to each other and they start without knowing which game it is, they usually do quite well across a wide variety of learning scenarios. Not equally well in all games. That's what we analyzed in this paper. But simple games like matching, pure coordination, or even stag hunt, they do quite well. Prisoner's Dilemma and Battle of Sexes, not so much. And you can kind of guess why. Right? Because when I take a good action and you take one, you discover through exploration, it's better for you to defect. So if you defect, my payoff falls too. So I change my action. So we can get locked into these iterative cycles of trying to figure out which actions both of us should take. But this is the first way to introduce the idea that just going from one to two actors who are both responding to each other can make learning by doing a lot more complicated. So we need a new language and terminology to talk about it. That's a coupled learning problem. Okay. So here we want to introduce one additional step, which is the idea that there is difference between dependence and between influence. So dependence is a situation where the outcome for J taking an action depends on the actions of I. That's our game theory model, right? What payoff I get depends on what others are doing. Or equivalently, you can say outcome J depends on both action I and action J, which is really saying outcome depends on which cell I land in. It depends on action I and action J. This is dependence. So what's influence? So influence is the idea that the belief of J depends on something that I does, independent of the outcome of J. Okay, so the belief of J depends on the belief of I or the action of I or the outcome of I or some combination of these. What it does not depend on is J's own outcome. That's pure influence. And we can embed this now into the learning cycles that we drew last time. You remember this picture? So actually, let me draw it up here on the board. That might be easier. Beliefs, actions, outcomes. Right? This is for actor I. Let's just call them 1 and 2. 1, 1, 1. And here's actor 2. So these learning cycles are clear, why they're drawn this way. Remember this from last time, right? That's what was in the model. That's what your model as well. So you start with some priors, you take action through softmax, you get feedback, you update through the updating rules, and then you take actions again, and the whole cycle goes through again. So when we think about interaction now between two actors, the first thing we want to do is say, where do they not interact, right? Which parts of their learning cycles are not going to be affected by each other? It's this part. So given the beliefs of each actor, the move from your private beliefs to your actions, we assume is not going to be touched by other people. Right? That's really saying that once you've formed your beliefs, you do your thing. So where do the effects of other actors come in? In the game theory models we saw, the way the effect comes is that my outcome, right? Let's take actor 2, depends both on this guy's action as well as my own action. Right? This is dependence. So what I showed you in the game theory matrices where I was showing dependence between actors, in a learning cycle model, this is what it looks like. Okay. So the outcome I get at any point is dependent on my actions and also on the actions of the other. And the same would be true in reverse for this person. So the outcomes for this guy depend on their own actions, but also the actions of this person. Right? So this is exactly the same as the game theory model when it is run over time through a learning cycle. Is this part clear before we go any further? This is pure dependence. They're not affecting each other's beliefs directly, right? They're not talking to each other. So can we think of situations like this? What would capture a situation like this where I'm not directly talking to you, but the actions I'm taking are producing some effect, which is partly dependent on what actions you're taking. And the same is true for you. So effectively, we are learning over time because we are playing these cycles again and again. That's where the learning is happening. And we are learning in a kind of joint way, in a coupled way, but not by talking to each other at all. There's no communication directly between us. So what would be an example of such a situation?
Maybe firm production.
Sorry?
Firm production in a industry. They're not talking to each other, but they're taking actions.
Okay, good. In fact, legally, they're not allowed to, right?
Yeah.
So there could be tacit collusion happening through this mechanism,
Yeah.
right? So interestingly, they might end up taking actions that look highly coordinated without ever talking to each other. Because in some sense, it depends on how you define talk. If talk is defined as an arrow from here to here, they're not talking. But are my beliefs affecting your beliefs? Yes, through the learning cycle, indirectly, right? That's what's going on. So yes, that would be a good example. Any other? Where else might we see this sort of mutual adaptation without communication?
So as in game theory, we see is repeated games is what is exactly what's happening. Like so, like a repeated Prisoner's Dilemma.
Yeah, any repeated interaction of this sort where communication is constrained. But like, what are some real life situations where communication is constrained, but our actions are dependent?
I'm thinking of like intergroup competition, like some groups in an organization, they compete with each other. Yeah, so they might not have the incentive to like communicate with each other, but they can learn from each other's action to decide their next action.
Okay, good. Let me help broaden it for you. When is communication difficult? The answer is actually always. Okay, perfect communication between people is next to impossible to achieve, right? Otherwise, all teachers would be getting 5.0 all the time and all students would be performing brilliantly. So communication is always constrained, okay, to more or less degrees. And particularly even within organizational contexts where everybody's, you can assume, incentive aligned, because they are specialized, they know different things, right? So the marketing people have a different skill set than the manufacturing people. The manufacturing people have a different skill set than the finance people. So even if they have every incentive to cooperate with each other, they're not in a prisoner's dilemma kind of situation. It may be more like a pure coordination game or a risky coordination game, or maybe a bargaining game. As long as communication is not perfect, this problem will arise. Okay, so it's actually very general. So for instance, one place where this happens a lot is in design. So if people are designing different parts of a technological system, it could be a car, it could be a software, it could be a computer, different design teams are working on different parts of the system. So they do their pieces, they put them together, they run the prototype, they get feedback, and they learn from that. But they cannot talk to each other perfectly because they are specialists, they are in different domains. So what's happening is exactly this kind of mutual adaptation, where there's no direct transfer of beliefs, but there's indirect effect through the actions on each other's outcomes. So this is quite general. It's not only about collusion in the market or groups which are competing. Those are good examples, but it can be much broader than that, right? Any situation where communication is constrained will have features of this. Okay, so this is a form of collective learning, which is called coupled learning, and it's coupled because there are dependencies between the actors. This is coupled learning. So one of the papers we read for today is a coupled learning paper, the paper I have with Swami. Okay. Now, what about influence? So let's take these arrows out and think about what influence might look like in this model. So what are some different ways in which one actor might influence the other? So how did we define influence? We said influence occurs when the beliefs of two, right, are affected by something that one does in a manner that does not involve this chain of action to outcome. So even if I were to shut off this entire portion from here to here, if I were to like turn this one off, there would be some changes here simply because of what one is doing. So what are some ways in which that can happen? One obvious way is I talk to you. That's influence, right? I might be directly able to talk to you and share my beliefs about how you should act. So if you're an apprentice, I'm an expert in some domain, I can sit down and explain, here's how I think you should go about modeling this thing, and I exchange my beliefs with you. So you have changed your belief without your going through your own action outcome cycle. Okay, this is belief sharing or knowledge sharing, if you want to call it that. But it could also be that I don't talk to you, I don't exchange beliefs with you, but I observe your actions or I observe your outcomes, or both. So what would be examples of this? Where I can
Vicarious
update my
learning?
belief. Yeah, these are forms of vicarious learning. So the point I'm really making is these are both forms of vicarious learning. This is vicarious learning through observation of either actions or outcome. This would be vicarious learning through belief sharing, right? But both are forms of vicarious learning because essentially I'm learning through the presence of the other without having to go through my own action outcome cycle, right? That's the key distinction. The world doesn't have to be this simple. All of this could be going on at the same time, right? It could be that we have coupled learning, plus we have learning our own doing, plus we also have vicarious learning through belief exchange, plus maybe outcomes and actions. So you can see how even with just two actors, right, given the dynamics of the situation, we can very quickly get into a lot of complexity. And this is where modeling starts to pay off, because it's very difficult to keep track of what's going on otherwise in this system. Because if you have it explicitly written down, then we can trace each channel and each path and figure out exactly what's going on here. Okay, so this is exactly the point. Vicarious learning is about influence. Coupled learning is about dependence. Okay, and vicarious learning itself can occur by sharing beliefs or by observing actions, observing outcomes, or both. Okay, that's the state space of possible ways in which two actors may learn as opposed to a single actor learning. And that's already increasing quite significantly the complexity relative to what we've seen so far. Anjul?
Yeah, Phanish. So you said there are like two types of vicarious learning, right? Mm-hmm. You are influenced by the actor one's beliefs, and you can also influenced by observing the actor one's actions and outcomes. What if there are like differences? So let's say, the vicarious learning, of course, but the actor two observes the outcome and action, mm-hmm. but you're still kind of influenced by the actor one.
Sure, I understand. Say that again. So you're saying actor two has his own actions and outcomes?
No. So what I think is, if you are not really communicating with actor one,
yeah,
and you just observe the actions and outcomes of actor one,
okay, and
you're saying you're still called the action outcome observation. That's vicarious learning.
Yes, because remember our definition of learning. Our learning is change in beliefs or behavior as a function of experience.
Right.
This is vicarious because of the experience of the other.
Okay. Oh, yeah. Thank you.
Right. But that's really the set of options on the table for different ways to think about vicarious and coupled learning. So we actually have a table from a paper that Sangyun and I have been working on. I will share that with you. Here you go. So this is your full set of possibilities all in one place. So think about I and J as ego and alter, to borrow language from networks. Okay. And here you have the two basic broad patterns of vicarious learning. So there can be belief sharing, where what is being shared is the belief from one actor to the other. And typically this requires a fairly high level of interaction, right? We need to talk to each other. We need to have a common language. We need to trust each other, I assume, for me to be able to pass on my beliefs to you. Some papers, including modeling and empirical papers, which illustrate this kind of vicarious learning. Or you can have just observational learning, in which you can have complete observation. So I can see action and outcome of the other, right? It's relatively moderate compared to belief sharing. I could just observe your outcome, okay? Or I could just observe your action. So if I just observe your action and I learn from that, that's imitation. And a lot of institutional theory models have this sort of learning process built into them. So diffusion of practices, for example, is a kind of vicarious learning which is driven by imitation, right? On the other hand, you can have inspiration, where I don't see your action, but I just see your outcome. So why do we call that inspiration?
It's something like an aspiration level thing, like social aspiration.
Okay, and the easy hint for that is when you see Hendrik's name on there, you can be pretty sure there's some aspiration level thing going on there, right? So yes, this is exactly the point. So remember, in these models, when you start out, you don't know the task environment, right? Which also means you don't know what the maximum is. So we know as modelers that you're stuck when you're getting a payoff of 0.9. You as the poor little agent don't know, right? You might be very happy with 0.9 until you see your neighbor is getting 0.95 and then you say, oh, maybe I should search some more. So that's the way in which even just learning through observation of outcome is also a form of vicarious learning. So the main point we want to drive home here is that there's a difference between dependence and influence. When only dependence exists, we have coupled learning. When only influence exists, we have vicarious learning. Vicarious learning comes in two broad flavors: sharing of beliefs or observation. Observation itself can be broken down into observing both action and outcome or just one alone, right? So you can already see from this that if we don't pay attention to these subtle differences, we can be talking past each other. Because if you treat all of this as one big bucket and call it vicarious learning, then I think we can end up with very confusing results and very confusing things to say. Okay, so I'd like us to think for a minute about examples where each of these is practical, and give me very concrete examples from organizational context where you see each of these things. Where might you see belief sharing? Where might you see complete observation or partial observation with imitation or inspiration? What are some situations?
I think belief sharing could be attributed to interlocks of board members. So
Okay.
yeah.
So they talk to each other, they have connections, they hang out in the same clubs or whatever, and they exchange beliefs about, is it a good idea to do golden parachute, something like that? Okay, that's nice. Yeah. Where would we see pure inspiration? Where I don't see actions, I only see outcome. There are literally tons of papers that have this, and we already talked about them today. This is social aspirations, right? The entire literature on social aspirations is really in that bottom row. It's a form of inspiration. So all I see is the outcome of the other, right? And that becomes the basis on which I construct my social aspiration. So that's the only element of vicarious learning necessary for performance feedback theory. The theory doesn't say the other things don't work. They just say you don't need them. You can already get performance-based feedback and learning and probabilistic search just by the vicarious learning which is happening in the bottom row, just observing the outcomes of the other. Okay. And what about imitation? Where do we see imitation processes where people can observe the actions of others, but not their outcomes or not necessarily their beliefs? What kind of situations correspond to that?
As in competitive situations where, as in, you know what actions the other has taken, but nobody knows if it will be fruitful in the future or not. I guess. Otherwise, it's difficult to dissociate actions or outcomes.
Okay, so competitive situations, yeah. More generally in benchmarking, right? So a lot of consulting companies make their money off benchmarking. In theory, benchmarking is supposed to show you both action and outcome. In practice, they don't. They just say we are going to copy the top 100 companies because they're the top 100 companies. But the actions they're taking may have nothing to do with their being in the top 100. So effectively, what you're copying is just their action. For example, agile teams. Okay, everybody and their grandmother is doing agile teams right now. So the benchmarking is to the top 100 companies. But unless you can show me that agile teams causes their high outcome and they're ending up in the top 100, it's pure imitation, right? So once you look closely at exactly what information is flowing between the actors, then we can understand if what's going on is belief sharing, is it complete observation, partial observation, imitation, inspiration, and the like. Okay, I want to take a pause now and get you guys to do some thinking. So now we have a framework for thinking about the difference between coupled learning and vicarious learning. And within vicarious learning, we have these different things. Now, how do you model coupled learning is obvious. I don't have to do anything really. I just take my basic model and I just change the task environment. Everything else can remain identical. Agree? Yes, no? Let me go back to the 4 elements of our models, right? All models always have the same 4 elements. So what I just said is in coupled learning, I only need to change the task environment. And how do I change it? I make payoffs to my action contingent on other people's actions. I use something like a game theory matrix, right? All the other steps can remain completely unchanged, right? That's coupled learning. The task for you is, I'd like you to think first on your own. Okay, let's take 5 minutes to think about this first on your own. How would I change the models to take into account vicarious learning? Any kind of vicarious learning. It could be either complete observation, partial imitation, partial inspiration, whatever. So first think about it on your own and write down maybe the equations, the way you would do it. How would we model vicarious learning in this setup? Okay, and you can use the learning cycles as a way to inspire some thinking about that. So let's think about that first on our own, and then we will try and work on it together. In fact, this might be not a bad idea to do it as a group for 10 minutes. Shall we try that? Let's see if I can actually throw you randomly into groups. Yes, I can. So let me create 4 breakout rooms. And I will assign automatically. Okay. So the agenda is, the question is clear. Based on these 3 different models of vicarious learning, 4 different models: belief sharing, complete observation, imitation, inspiration. How would you model them? By tweaking the basic model of learning by doing that we've been working with so far, right? Before the break, we talked about how to tweak that model to incorporate performance feedback and aspiration adjustment. Now we want to incorporate vicarious learning of these 4 kinds in that model. How do we go about doing that? That's the question. So I'm going to bring you back in 10 minutes. Okay, looks like everybody's back. So who'd like to go first? So the question again, to refresh your memories, in case there was question drift over time in the groups, is how would you model vicarious learning within this framework? And the answer I'm looking for will tell me exactly what I would change in each of these 4 basic elements of the model, right? So we want to know, like, how would I change the task environment? How would I change the representation? How would I change the choice process? How would I change transformational representation? Okay. All right. Who'd like to go first?
I can try.
Go for it.
So, Zhang Yong and Tian Cheng and I, we discussed that because the vicarious learning, it mainly affects my beliefs. So we think we don't need to change the task environment. And then the main thing we want to change is the updating process, like the transformation of your representation. Yes, this part.
Okay.
So for example, if it's the first case where my beliefs is affected by the others' beliefs, we can like update this pie according to the other agents pie. But we do have a discussion about like how we update, like are these 2 agents compromise between each other's representation, or is it just like one learning from the other? That will create some differences. And then in terms of action, we think that there might be a difference in the time. For example, at time t, I may adding the action of the other agents taken in time t-1, and then assign a higher payoff because he takes that action. And then in terms
hang on. Let's go to the action one in a second. Let's stick with the
Okay.
belief one. So that's very interesting by itself. So something like this is what you have in mind, right? So my belief, agent I, at time t is like my past belief.
Yep.
And I'm no longer writing the K for the particular action. I'm taking the entire vector of actions, right? So these are vectors.
Yep.
So I'm going to take my entire vector of actions, take the beliefs for them in previous period, take your beliefs in the previous period.
Yes.
And somehow combine them to get my new belief.
Yes.
Okay. How do I combine them exactly?
Yes, that's the discussion we have. Like, for example, we can take like the average between these 2. So it means we are compromising between like the 2 agents' perspectives.
So there's a general way of doing this. So your instinct is absolutely correct. And this is called de-grouped averaging. The only difference from what you said is that it doesn't have to be simple. It's a weighted averaging. Okay, it doesn't have to be half and half. Okay. Now, if you look at this equation, what is W telling you? How do I interpret W?
It's how much do you learn from your own experience
versus the other, right?
Yes.
So this is really a measure, if you like, of how open I am to social influence. So suppose W is 1. That means I don't pay any attention to what you're telling me, right? If W is 0, it means I only pay attention to what you're telling me. I don't put any weight on my own belief. Some number in between would tell me something about the relative weight I put on your beliefs versus mine, right? It's quite an interesting and rich parameter because inside W, you can hide things like status, like hierarchy, like authority, right? Like sense of expertise. Or you can hide things about the person themselves, like how socially influenceable are they? Are they autistic, right? There are many things we can hide in that parameter. But this is really the point about how do I combine the beliefs of others with my beliefs to form my new beliefs in the new period, okay? Before we open it up to further questions, I want to see how other groups dealt with this question. This is, I assume, after they've first done their own individual learning. So that's T-2, right? Plus P times the payoff that they got from the environment minus the private belief they had at T-2. So in other words, first you do learning by doing, and then you do vicarious learning. That's how you thought about it? So I'd still do my learning by doing is the point, right? You would still go through the process of first taking my action, then updating my belief based on the payoff. But before I actually update my beliefs to the next period, I take my old period payoffs and I weighted average them with you. And now I'm ready to go back to the cycle of learning by doing. Right? That you need to account for both, basically. That is the key point. So both learning by doing is happening as well as social learning from the other. All right. So let's hear from other groups and other thoughts on just this belief sharing idea. Did you converge to something similar or something different?
Phanish, so Shukti, Jennifer and I discussed a very similar approach that just Nettie presented. But we would argue that this learning can happen even before doing something.
Okay.
By just sharing some belief, especially some information sharing by the other party. Mm-hmm. So we will focus more on the stage of representation of test environment, which consists of these two parts: the set of alternatives, and the other one is the expected performance outcomes. But we more like to say that the set of alternatives is more like a fixed variable to the agent, whereas this expected performance outcomes can be impacted even before you take any action by just hearing some others' opinions or feedback. So you first update this expected performance outcomes here, for example, using almost the same function. Like pi1 can be updated by taking the other person's belief into consideration. But as Nettie just elaborated, there can be some weight parameter, which is like a W and 1 minus W, for example, how much I would take this person's belief into consideration seriously. So through this process, we first update our expected performance outcomes before even taking any action. And then we take action, see if like whether our updated belief makes sense or not. Yeah, this is what we discussed.
But is that the same as saying we just kind of, if you were to repeat this many times, effectively that's what will happen. But in addition, what you're saying is in the first period, you start here rather than here.
Right.
And I like that, because remember last time, one of the questions we had was, where do priors come from? Right? And this could be a theory of where priors come from. So they come from mutual discussion among ourselves, and we start there. And then based on those priors, then we take actions, then we again discuss, then we take action, take discussion, right? So it's iterative. So in the end, across many periods, it may not matter that much, but your priors will be affected by this. So that's an alternative way of thinking about it. Yeah.
We discussed the example of socialization, like when new starters join. And so that's where their priors come from, the socialization process. So that's why.
That can be very effective. Exactly. So it will have a big difference on your priors, whether you start, right, at the beginning with private priors or with common priors. And the learning process will look different. But after that, the iteration will essentially make these two things equivalent. But in the first period, it can make a difference. Absolutely. Other thoughts on how to approach belief sharing? Any other ways of doing it? This is still fairly broad, right? Essentially, I'm taking everything you believe, everything I believe, and averaging them. Can we be more like subtle, discriminating? So I may believe you're a very smart person, but maybe not on everything. So I don't have to take your entire bundle of beliefs about the world. How would I think about that in this framework?
As in, then like something like specialization would come into consideration, where for certain actions you are updating belief on based on the others, but for other actions you're not.
Okay, so exactly. So I suppressed K here, but I can bring it back here, and I can say for certain actions I do this. So the W can be case specific. So the W can have a case specific subcomponent. So I'm very open to listening to things where I think you're an expert, and on the others, I think I'm the expert. I won't listen. Okay, we can take it in other directions like that, but this is clearly one sense in which we can operate with this basic setup. Okay, anything to add on belief sharing, or shall we turn to observation learning? Everybody else converges on the same basic approach? Okay, so that's good. So it's good for you to know that you have actually rediscovered degrowth averaging. Okay, it's very obvious. This is what you would do, but it is known by this guy's name because he did it first. And what is nice is that there's a lot of very good empirical evidence showing that this fits the data really well. Okay, the literature which looks at this using degrowth averaging is called opinion dynamics. and I can give you some citations to recent papers which have actually calibrated these models, and these tend to fit the data extremely well. Okay, so this is a pretty good approximation of what happens when people talk. They kind of converge somewhere in the middle through conversation. Now, one interesting property of degrowth averaging to point out, which is actually very interesting. Think about a case where, let's say, agent 1 has a belief structure like this. Okay, this is action 1, action 2, action 3. So for him, this is number 1, this is number 2, and this is number 3. Let's say there's an agent 2 who has a belief structure that looks like this. Okay. Through their averaging, it could be that they end up taking an action which was not the best for either of them on their own. They may produce a third action, which is now the winner, because these two are canceling out. Right? When you average them out, the high and the low, when you put them together, they will like flatten each other out. So one interesting property of degrowth averaging is that it can lead to emergent outcomes, in the sense that actions can be taken which were not top in my list, not top in your list, but now they come to the top. Okay, that's the general property of degrowth averaging, which is very interesting. Another property of degrowth averaging, which just comes from the property of averaging, is our beliefs through this process will not only become similar, they will also become fuzzier. So I haven't defined fuzziness, right? So what is fuzziness? Fuzziness is the delta between the highest belief and, let's say, the next highest one, or the lowest one, doesn't matter, right? But the point is, if you have beliefs which are very spiky, so you think one of these things is much better than the other, then you have a high resolution belief. If all your beliefs are kind of equally the same, then you have a fuzzy belief structure. You're kind of indifferent between actions. So degrowth averaging is a process that actually turns beliefs into fuzzy beliefs. So the more similar we become, at the same time, we also become fuzzy. That's the implicit assumption when you average, right? That's what you're doing. So it fits the data quite well. But can you think of situations where this may not be true? Where averaging not only produces similarity, but preserves the sharpness of the beliefs. Mechanically, it won't happen, because when you average, this is bound to happen, right? It's going to even out. But can you think of social phenomena where through social influence, you get not only similarity in beliefs, but are able to preserve the sharpness of beliefs?
If it's a hierarchical, for example, the boss orders the subordinate to do something, the subordinate will take whatever the boss believes.
But that's the same as W equal to 0. So then I don't increase my sharpness. I can keep it the same. That's what you're saying?
Yeah.
Yeah, you're right. Absolutely. So yes, I can keep the sharpness of my beliefs, the resolution the same, because essentially I'm not averaging, right?
Yeah.
What I'm doing is really just transforming my beliefs to their beliefs.
Yeah.
There's no weighted averaging going on. That's one limit case. Yes, that's right. Any other phenomena where you might see something different, where you don't see a evening out, but you see maybe a sharpening up? Think about confirmatory bias, right? So you can imagine a world in which we first compare our beliefs and it turns out they're very similar. Then we actually strengthen them even more. Okay. Instead of averaging and flattening out, we might actually model a process where we first compare our beliefs, and if we look like we believe in the same thing, we become even more confident. So we can get confidence from interaction, from social influence as well. Okay. That's not captured in this. This just mechanically forces a process where beliefs become similar and at the same time they become fuzzy. So this is not the last word on how to do social influence or belief exchange. It's one very popular one. And the good news about it is the evidence seems to back up this as being a pretty good model of what happens when there is social influence. Okay, let's move to observational learning. So can I get a different group to give it a shot? How would we model, for instance, observation of actions?
So isn't what we discuss, Hangjun, Jungyo, and Chuping is that you're basically looking at somebody's actions, and you're basically updating the belief that that's the most effective.
So as an equation, can you give me some help on how would I translate it into this equation? Let's say.
Yeah, as in we as in when we were discussing, we were thinking it at the transformation step, that when you are looking at and that's where you are basically updating your belief that what the other is doing is.
But this is the transformation step.
Mm-hmm.
So how would I use, or how would I incorporate in this the idea that I think somebody else's action is actually the right one to take?
So the learning would be 0, and then you are converting the belief of what the other is doing is as the maximum. So you're taking that and making it 1.
So let me reintroduce the K notation, because this may be otherwise confusing. So the full correct way to write it as it was there in the slide, remember, was I had the specific action, right? Yeah. Remember, reinforcement learning only updates the action you took. So if there are 5 actions, you're only updating the 1 action you took. Why was that? Own action dependence, right? That's the basic condition of a reinforcement learning task, that you only get feedback on the action that you took, and therefore you only update the action that you took, right? But now with observational learning, I will write this kind of equation twice, once for the action I took and one for the action you took, right? So I would also be updating the action that you took, which could be, let's say, not J, but let's call it something else, K2, let's say. Mm-hmm. So I'm going to update my belief about the action you took, not the action I took. But the trick here is, I don't actually know what your payoff was, because I only observe your action, right? So I've got to impute something for pi. Stop working. So I've got to impute some value of pi, right? Mm-hmm. Which is really going to tell me how attractive do I think is the action that you just took. I don't know how good it was, because I can't see your outcome. But effectively, I got to assume some number. So let's assume for simplicity that it's the max that you can get, which is 1, right? Yeah. So effectively, what it is I'm updating not only my action using the standard formula, I'm also updating the action I didn't take, you did, by using my old feedback, my old belief, plus again some learning parameter, which need not be the same as this one, but we can make it the same for the moment. Some payoff, maybe 1, minus my old belief. Okay. So by adding this, I have essentially incorporated a model of observational learning based on just observing action. This is imitation. And the reason it's imitation is because I actually don't know how well you did. This is blind benchmarking. I'm just assuming it's 1, right? That's the sense in which it is like benchmarking. So this is a way to capture observational learning on action alone. Any different views on how we might do it? Any other ways you came up with? Yeah, Pulkit, go ahead.
So the way we thought it was that the benchmarking is already influenced by a person who's looking at it. So it's some kind of function of the person who's looking at it, already a function of pi of I, not like 1 or something. So yeah.
I'm not sure I understand. Can you explain?
So when we are doing this benchmarking here, you took the benchmarking to the maximum 1.
Yes.
Yes. So what we did was, this thing is already a function of pi, the original one, the one above, the person who's taking his action. Yeah, the person who's watching.
That's the payoff I got for my action. Yeah.
Yes. So some payoff that you already think you can get from this action.
No, hang on. This is the payoff I actually received when I took action K1.
So it's pi, right? I mean,
yeah, it's capital pi. Yeah, there are 2 pi's here, but this is the big pi. Sorry.
Okay.
I'm using pi for both, but let's think of this as payoff. Let's just call it payoff.
Okay.
This is your actual payoff. Yeah? Let's call it P.
Okay.
Yeah.
So what we thought, this thing, the way it would be updated would be some function of the payoff that observer is expecting from that function. If observer does that thing, and then this thing happens. This one is a function of small pi.
That is my expectation of what would happen if I took this action.
Yes, so this will also be a function of that, and then.
But then this will cancel out and become 0.
No, some fraction or something like that.
So you want to multiply this by some number which will make it towards 1, but it does not want to make it 1. Yeah. Okay, got it. Okay. That sounds detailed. Okay, I'm not sure we need that much super detail here. But essentially what you're saying is we can parameterize the extent to which I believe your action is going to lead to a good outcome.
Yes.
That's what you want to say. Okay, that makes perfect sense. Yes. So I just took it to the limit case where I think it's perfect, but I don't need to be that optimistic about your action. I can say it's just going to be better than what I had. Right? But the other way to do it, what you just said, I could also accomplish by keeping this at 1, but changing this. Yeah, you see that? So I can just play with this parameter. So right now I assume that my update rate is the same for my own action and from learning from others. Why does it have to be? Doesn't have to be, right? So I can make this one much smaller than this, which would effectively get me to what Pulkit wants. Okay, different ways to do it. So the mechanics of how to do it can vary, but I think the basic logic, if it's clear that when you observe action alone, right, only observe action, then you need 2 equations. One which updates the action you took as before, one which updates the action the other person took, but with the additional complication that I got to make up some expectation about payoff because I don't see it. Right? I don't see it. So I have to find some way of assuming something there and then plug it in. Any other variants on this, or this is pretty much how we converge on this?
I have one question regarding the imitation. I was wondering whether it is possible that your representation has not changed, but you only imitate others, so you only change your choice. I mean, the choice is a function of your own representations and the other ones, others' choice. I just wondering whether it is possible.
So you remember when I drew the learning cycle, I said the one part that doesn't change is the link between my belief and my action. Right? So in the end, your actions are always going to be based on your beliefs. So what you're proposing is to maintain 2 kinds of beliefs, one which I privately hold and one which I publicly hold.
Okay.
Right? Is that what you're saying? So I kind of privately still don't believe that what you're doing is the right thing, but I'm going to do it anyway because I want to fit in or something like that. Is that the idea?
Yeah.
Yeah, but that is equivalent to saying I maintain 2 sets of beliefs. One, privately in my heart of hearts, I know what I should do, but because I want to fit into the group, I'm going to do what everybody else is doing, right?
Okay.
So we can do that. That's possible. But effectively, another way to make it simple is to say both of those converge into one set of beliefs, and that's what's driving this. So this is like the net effect of my own private belief plus what I think I should do to fit in. And the combination of that is being captured here.
Okay, got it. Thanks so much.
But there might be situations where it makes sense to separate those. And you could do it. I don't think there's anything wrong with it. But the simplest possible way to do it is something like this. Okay? All right, last one. How about the case where we don't observe action? We only observe outcome. What do I do now? How would I model that? This is pure inspiration-driven vicarious learning. This is a weird one, right? Because I have my action updating going on, but I don't know what action you took. I don't have access to your beliefs. I just see that you got a payoff. So the only information I really have is this is my payoff. I have your payoff. What do I do with it?
Couldn't we still do it by deciding an update rule for our aspirations? So
good. So it's not going to work by updating my belief about a particular action, right? Because I don't know the action. But it has to work in some other way, and the best candidate for that is aspiration, right? But we can skip aspiration and directly go to the effect of aspiration in our model, which is through tau, through exploration. So we can say that when I see other people doing better than me, maybe I should be exploring more because my belief structure is not showing me payoffs like this. So one natural place to hook up from here into the model would be to use this to update tau in some way, or you could do it intermediately first through aspiration. But in our baseline model, there is no aspiration. Remember, in the basic adaptive reinforcement learning model, we don't need an explicit aspiration. So the easiest way to connect it would be here. But if you want, you can do it through here and then link it to this.
yeah, and so actually update tau by saying we will assign this much weightage to my own historical performance and that much weightage to social, or like
exactly.
Yeah, basically divide like how much weightage I give to my own previous period performance versus how much weightage I give to observed.
Observe. Yeah, that's certainly one way to do it. Other thoughts? How else could we incorporate the observation just of the payoff of the other?
As in, we discussed something that we discussed in the class before about when you were talking about performance feedback, that we could still sample the, as in once we update the aspiration level, we know that the second thing that we can do is we can sample the task, the task space even more. So we have something that we already
like this, no? It's moving through.
No, but the search space, as in we have certain actions that we know, but we could still expand.
You guys are now combining two models at once. Right now, we're just talking about the basic adaptive reinforcement.
Okay. Yeah.
Right? So just in the ARL, what would you
Yes.
change is the question. But yeah, if you were to also first add the aspirations and search to ARL, and then add observational learning, then yes, what you said would go simple. Okay, the heuristic in this thing is there's already so much complexity, right? I just showed you by adding one agent more. Our world has already become so much more complex because we have to distinguish coupled from vicarious. Within vicarious, we've got to think about 3 different kinds. The math for each is different. So one step at a time. Baby steps is the operating. Okay. But yeah, the intuition is good. That's how we should do it. Sangyun, I can't remember now. Is this how we did it in our paper? Exactly like this? Good. So the class has validated our intuition. That's not bad. So maybe we didn't get it wrong. So we actually have a paper where we model these 3 different things and we have results that show you under what conditions these things work and so on. But this is pretty much it, right? So now you have a formal framework to think about learning by doing, okay, coupled learning, and vicarious learning. All 3 can co-occur, but that is a very complicated problem. So what has been more typical is to do 2 out of the 3. So individual learning by doing plus coupled learning. That's easy. That was the Puranam and Swami paper you read. Individual learning by doing plus vicarious learning. That is what you saw in the complexity paper that Sangyun and I shared with you, right? So these are ways in which we can go from the basic learning by doing model, but add these. But what is really powerful, and hopefully you can see, is that these can all be accommodated as extensions of the basic ARL framework. Okay, if you master that, then these things are like tweaks on it. It's like turning knobs and switches here and there, and you can get all kinds of variants on this. So I would recommend you try some of these things out for yourself. I mean, again, you don't need to for the replication part, but just for some fun, you can try and see what happens. Just take the standard model, add 1 more agent. You don't need to change the task environment, stick with vicarious learning, and then see different belief sharing rules, what kind of effects they have, or different observational learning rules, what kind of effects they